Well, hello and welcome to our first higher level chemistry topic. So let's get straight into it, and we're going to start looking at redox calculations. So for the higher level content for this topic, which is topic 19, okay, there's just a little bit of maths that we need to add in on top of our understanding of voltaic cells and electrolytic cells. So let's get started. The first part that we're going to do is be looking at calculating E0 values. Okay, so essentially this all stems from understanding how when we put metal in contact with a solution of a salt of that metal, it produces a electrode potential. Okay, and we talked about there being a potential difference between two half cells, and that's how we generate electricity. And essentially now what we're looking at is that we need to be able to explain the size of this electrode potential in terms of the reactivity of the metal. So how easily the solid metal will release electrons and how more reactive metals will have what we call a higher electrode potential. We need to be able to understand that this was standardized against, of course, like most things in chemistry, a reference standard, and this is the standard hydrogen electrode, which we've already talked about. We also need to understand that standard electrode potentials being measured against this standard hydrogen electrode, it's been given a value of 0.00 volts. And then, of course, because we're putting the maths into it, we have to be able to actually complete those calculations to be able to tell what the electrode potential or the voltage that a cell will be. So let's get started. This is all basing around the idea of electromotive force, or EMF, which is the potential difference generated by a cell. Okay, so this idea here that the reactants and the products share a difference in energies, so there will be a potential difference. This thing here, which is Gibbs free energy, if you read through in your textbook, you will notice that there is a mention of Gibbs free energy in this unit. We'll come back and look at it more when we do higher level energetics. So essentially what we're saying is that the voltage of the cell, okay, depends on the difference in the tendencies of two components to undergo reduction, i.e. the difference that they are apart on the electrochemical series. So how strong a reductant, how strong an oxidant they are. This can only be measured experimentally. There's no theoretical way for us to understand oxidizing or reducing strengths from many of our bonding models. So we measure these experimentally, just like you did in the experiment the other day when you had to work out your own reactivity series with the voltaic cells. So these generate the electrochemical series, and that we know and love, this one here, table 24 in our data booklet. So just a reminder that our standard hydrogen electrode, we have hydrogen gas at 298 Kelvin and 100 kilopascals, bubbled through past an inert platinum electrode. There's an acid solution which contains 1 molar hydrogen ions, and basically this glass tube allows H2 gas to escape, so the pressure doesn't build up. But here we see, according to our electrochemical series, hydrogen is in fact given a value of 0, and everything else is measured relative to hydrogen. So the standard electrode potential is given by the symbol E0, and you may have noticed these down your electrochemical series. So on the right hand side here, these E0 values, this is what we're going to learn to deal with today. So E0 values are given by the reduction reaction. So they're the standard reduction potentials. So as we move down the electrochemical series, we increase the tendency for the reaction to occur as a reduction reaction. Okay, which makes sense because as we move down the electrochemical series, right down the bottom are our strongest oxidants, and they will be reduced. So, E0 values refer to the reduction reaction. They do not depend on the total number of electrons, so they don't have to be scaled up or down according to stoichiometry. So if it's 2 silver and 1 copper, we're not going to multiply the E0 value of the silver by 2. Okay, so these aren't influenced by the coefficients or the stoichiometric ratio of our reaction. The more positive the E0 value for a half cell, the more readily it is reduced. Okay, so the higher the positive number, the more likely it is for that forward reaction to occur. So The half cell, when we calculate cell potential, or E0 of the cell, so it's E0, so E to the superscript naught, subscript cell, what we're doing is we take the higher E0 value, or the more positive, so the one further down our electrochemical series, that will be reduced, okay, and the more negative one, the one higher up on the right hand side, is going to be oxidized. So if we want to work out the potential difference, or the E0 for the cell, we take the E0 of the reduction reaction and subtract the E0 of the oxidation reaction. Okay, so what this will generally mean is that we take the more positive value and subtract the less positive value, or in many cases this will be negative. So when we subtract a negative number, of course, we will be adding. So if we have a positive E0 value, the cell will be producing electricity. Okay, let's have a look at this one. We can see here that the voltmeter is giving a reading of 0.46 volts, much like the situation we've seen in the lab before. So if we want to work out the E0 of the cell, we look at the E0 of the reduction reaction and the E0 of the oxidation reaction. So first we need to figure out which is which. In this, we have silver, we have a silver nitrate half cell, and we have a copper nitrate half cell. So we go over, we have Cu2 plus and Cu solid, Ag plus and Ag solid. Of course, the spontaneous reaction is going to be this one. So we're going to go forward. So Ag plus to Ag solid is the cathode, which we confirm here. It'll be the reduction reaction, and then Cu solid going to Cu2 plus is going to be my oxidation at the anode. So if we take our reduction reaction, which is plus 0.8, and we now subtract our oxidation reaction, minus 0.34, our answer, of course, will be 0.46, and that is the voltage, or the potential difference of that cell, so the voltage that we will observe when the cell is discharging. Okay, so if we connect the zinc electrode to the standard hydrogen electrode, okay, what we will find, so we've got hydrogen here, we've got zinc here, have a quick flick back to our electrochemical series. So what we're looking at is zinc compared to our hydrogen electrode, and we can see that zinc is negative, so it's going to be H plus and Zn solid. So hydrogen is going to be my reduction half cell, minus the negative of my zinc half cell is going to give positive 0.76 volts. So this reaction will occur spontaneously, it will generate electricity, and it will generate electricity with a potential difference of 0.76 volts. Essentially, we can use this to determine spontaneity, i.e., will the reaction be spontaneous? Okay, again, spontaneity is generally something that we'll look at more in HL when we talk about Gibbs free energy, but for now, if E0 of the cell is positive, the reaction is spontaneous as written. Okay, which means that in that case you have correctly identified the cathode and the anode, and that reaction will occur spontaneously. If it is negative, then it is a non-spontaneous reaction, and we would need to put energy in, i.e. electrolysis, in order to force that reaction to occur. Okay, so that's what we mean by spontaneity. So if we have a look at this, we have a nickel and manganese 2 plus ion solution here. We can look at them according to their E0 values. Okay, so in this case, the manganese 2 plus and the nickel, if we assume that the manganese 2 plus is going to be reduced, then we will see that we'll have a negative 0.93 EMF or E0 value. Because of the negative sign, it tells us this reaction won't happen spontaneously. We're not going to get nickel 2 plus at being oxidized and manganese being reduced. Okay, so in the mixture, the reaction that will occur will be the reverse reaction. We will be reducing nickel and oxidizing manganese. And you can see that kind of makes sense because nickel has already lost its electrons, so it can't really be oxidized anymore. And manganese has electrons to be able to donate, so it makes sense that it would be oxidized. When we compare oxidizing and reducing strengths, this is exactly the same as what we've done on the electrochemical series before. The strongest reducing agent or reductants are in the top right-hand corner, and the strongest oxidizing agents are in the lowest left-hand corner. Okay, and we can see that metals with low E0 values are the most negative and the strongest reducing agents. So the more negative, the stronger the reducing agent that it is. Okay. So we can have a look at another example. A solution containing potassium permanganate 7 and concentrated hydrochloric acid reacts to form chlorine gas. Identify the strongest oxidizing agent in the solution and calculate the standard cell potential. Okay, the strongest oxidizing agent is our strongest oxidant. Okay, so it will be the one that is reduced. Okay, so it has the higher E0 value, which is our MnO4. Okay, which means that it will be reduced. Chlorine will be oxidized, so therefore reduction will be the MnO4 minus 1.51 minus the 1.36 of our chlorine reaction, so the overall voltage will be 0.15 volts. Just a quick note, and I know a couple of you have already started to realize this and there's been some questions about it. The E0 value, or the position on the electrochemical series, gives us no indication of rate of reaction. It tells that the reaction will be spontaneous, but it doesn't tell us how fast the reaction will be. So it could be a spontaneous reaction, but it may only occur in a few molecules per every hour, and therefore we wouldn't be able to observe that change in the short period of time. Or the E0 values also don't tell us anything about non-standard conditions. So if it's outside of SLC, so different temperature to 298, concentrations are increased or reduced, and the pressure is different, we can see changes in the position of the electrochemical series. So there are limitations to our use of the electrochemical series in terms of we need to be aware that in non-standard conditions, the reactions may not occur as predicted, or that we may not see the reaction if its rate is too slow to be observed. Okay, so we need to be aware of these limitations. And I'm going to leave this video here before we move on to the next calculation with Faraday's laws.